In 1950, astronomer Art Hoag was scanning photographic plates from the Mount Palomar Observatory when he noticed something that made him pause. Among the thousands of galaxies captured on film, one stood out as impossibly strange. It looked like someone had taken a galaxy, cut out its middle, and replaced it with empty space, leaving a perfect ring of stars floating around a separate, spherical core. The two structures seemed suspended in space with nothing connecting them, defying every known model of how galaxies form and evolve. Hoag's object, as it came to be known, sits roughly 600 million light-years away in the constellation Serpens. From Earth, it appears as a near-perfect circular ring of young, blue stars encircling an older, yellow core. The gap between them is so clean and symmetric that early observers wondered if it might be an optical illusion, perhaps a foreground galaxy coincidentally aligned with a background object. But deeper observations confirmed the impossible. Both the ring and the core belong to the same galaxy, moving together through space, yet separated by a void spanning thousands of light-years. For decades, astronomers struggled to explain how such a structure could exist. Galaxies are supposed to form through gravitational collapse, with matter spiraling inward to create disks, bulges, and arms. They grow through mergers, with smaller galaxies crashing together to build larger ones. Nowhere in the standard models of galaxy formation was there room for a galaxy that looked like a cosmic donut, a structure so geometrically perfect it seemed more like an artifact than a natural object. Hoag's object challenges everything we know about galactic dynamics. Its ring rotates at speeds that suggest enormous mass, yet the gap between ring and core contains almost no visible matter. The core itself is composed of old, red stars, typical of elliptical galaxies, while the ring blazes with young, blue stars still forming from fresh gas. How did these two populations end up in the same system, separated by such a vast emptiness? Why does the ring maintain its circular shape instead of spiraling inward under gravity? And why, in a universe of trillions of galaxies, do we see so few objects like this? The answers lie at the intersection of collision physics, dark matter dynamics, and the hidden mechanisms that govern how galaxies evolve over billions of years. Hoag's object isn't just an oddity, it's a window into processes we're only beginning to understand. A cosmic experiment frozen in time, revealing secrets about the forces that sculpt the universe's largest structures, the discovery that defied classification. Art Hoag wasn't searching for anomalies when he found his namesake object. In the mid-20th century, astronomy was undergoing a revolution driven by advances in photographic technology. Large telescopes equipped with sensitive photographic plates could capture faint galaxies millions of light-years away, and astronomers spent countless hours examining these images, cataloguing objects, and classifying them into known categories. Spirals, ellipticals, irregulars. The Hubble sequence provided a tidy framework for understanding galactic diversity. Then Hoag's object appeared, and the framework broke. The object showed up on plates from the Palomar Observatory Sky Survey, a massive project that aimed to photograph the entire northern sky visible from California. Hoag noted its unusual appearance in his observational logs but was cautious. Photographic plates could introduce artifacts, dust, emulsion defects, or overlapping exposures that created false structures. He initially suspected the ring might be a gravitational lens, a phenomenon where a massive foreground galaxy bends light from a more distant object, creating multiple images or distorted arcs. Albert Einstein had predicted this effect decades earlier, and by the 1950s, astronomers were beginning to recognize its importance in cosmology. But closer examination ruled out lensing. A gravitational lens produces multiple, distorted images of a background source, and the geometry depends on precise alignment between observer, lens, and source. Hoag's object showed no such multiplicity. The ring was singular, symmetric, and rotated as a coherent structure. Spectroscopic analysis, breaking down the light into its component wavelengths, revealed that both the core and the ring shared the same redshift, meaning they were at the same distance from Earth. They weren't separate objects aligned by chance. They were physically connected, part of a single galactic system. The symmetry was the most troubling aspect. Galaxies are messy. Spiral arms bend and fragment. Ellipticals show lumps and asymmetries from past mergers. Even the cleanest disk galaxies display warps, bars, and irregularities when examined closely. Hoag's object, by contrast, was nearly perfect. The ring measured roughly 120,000 light-years in diameter, with the core sitting almost exactly at its center. The gap between them spanned about 10,000 light-years of near emptiness, a void where visible matter seemed absent, yet something had to be holding the structure together. Hoag published his findings in 1950, but the astronomical community remained puzzled. It wasn't a spiral, though the ring resembled spiral arms stripped of their central disk. It wasn't an elliptical, though the core had that appearance. It wasn't a merger remnant, which typically shows tidal tails and chaotic distributions of stars and gas. It was something else entirely, a ring galaxy, a category so rare that Hoag's object remained the only confirmed example for decades. The classification problem went beyond taxonomy. Understanding how galaxies form and evolve requires models that explain their shapes, structures, and dynamics. Spirals form when rotating gas clouds collapse into disks. Ellipticals result from major mergers that scramble stellar orbits. Irregulars reflect gravitational interactions or insufficient mass for organized structure. But ring galaxies? No theoretical framework existed to explain them. Hoag's discovery implied that galactic evolution could follow pathways completely outside the standard models, pathways so rare or transient that we'd barely glimpsed them. Astronomers debated several possibilities. Perhaps the ring was a transient feature, the result of a recent collision that would eventually collapse or disperse. Perhaps it was an edge-on-disk galaxy with unusual opacity, making the central regions appear detached. Perhaps it was a statistical fluke, a 1 in a billion configuration that would never be fully understood. Each hypothesis had problems. Transient features should show signs of disruption, tidal tails, streaming gas, shock fronts. Hoag's object showed none. An edge-on-disk couldn't explain the ring's rotation curve or the spectroscopic separation between core and ring populations. And statistical flukes don't predict anything. They merely label ignorance. The mystery deepened with technological advances. By the 1970s, radio telescopes revealed that Hoag's object contained significant amounts of neutral hydrogen gas concentrated in the ring, fuel for the ongoing star formation visible in blue light. Infrared observations showed that the core was composed of old, red giants, stars billions of years old, formed when the universe was much younger. The contrast was stark. An ancient core surrounded by a youthful ring, separated by emptiness yet bound together by gravity. Follow-up observations using larger telescopes confirmed that the ring wasn't an illusion or artifact. High-resolution imaging from the Hubble Space Telescope in the 1990s captured stunning detail, revealing individual star clusters within the ring and confirming its three-dimensional structure. The ring wasn't a projection or a trick of light. It was real, a massive annulus of stars and gas orbiting a central core, maintained by forces that remained unexplained. The Hubble images also revealed something unexpected. Another ring galaxy visible through the gap in Hoag's object, located roughly 10 times farther away. This serendipitous alignment showed that ring galaxies, while rare, weren't unique. Somewhere in the universe's history, processes existed that could sculpt galaxies into these bizarre structures. The question was no longer whether Hoag's object was real, but what sequence of events could create such an improbable configuration and why we see so few of them. The ring's impossible perfection. When astronomers measure the symmetry of Hoag's object, the numbers reveal something unsettling. The ring's deviation from a perfect circle is less than 3%. In galactic terms, this is extraordinary. Even the most regular spiral galaxies show asymmetries of 10 to 20%, caused by gravitational interactions with nearby galaxies, internal density waves, or the uneven distribution of dark matter. Hoag's object, by contrast, maintains a near-perfect circular geometry despite being hundreds of millions of years old. This perfection poses a fundamental problem. In astrophysics, symmetry typically reflects equilibrium, a state where forces balance perfectly, allowing structures to maintain stable configurations over long timescales. A spinning disk of stars and gas naturally forms an ellipse if rotating rigidly, or a spiral if density waves propagate through it. But rings require specific conditions that are difficult to establish and even harder to maintain. Consider the mechanics. The ring in Hoag's object contains massive amounts of material stars, gas, and dark matter all moving in roughly circular orbits around the central core. For this structure to persist, the gravitational forces must be finely tuned. Too much mass in the core, and the ring would spiral inward, collapsing onto the center within a few 100 million years. Too little, and the ring would expand outward, dispersing into intergalactic space. The current configuration suggests a delicate balance, but how that balance was achieved remains mysterious. Spectroscopic measurements reveal another layer of complexity. The ring rotates differentially. Inner portions orbit faster than outer portions, following a velocity profile similar to that of spiral galaxies. This differential rotation indicates that the ring isn't a solid structure, but a collection of stars and gas clouds moving independently, held together by gravity. Yet despite this independence, the ring maintains its circular shape without fragmenting into clumps or developing the spiral arms typical of disk galaxies. The ring's stellar population adds to the puzzle. Observations show that the stars in the ring are predominantly young and blue, with ages estimated at a few 100 million years. This implies recent star formation, fueled by gas that somehow accumulated in the ring. But where did this gas come from? Galaxies form stars from cold molecular clouds that condense under gravity. In normal galaxies, these clouds are distributed throughout the disk, forming stars gradually over billions of years. In Hoag's object, star formation is concentrated exclusively in the ring, suggesting that gas was either funneled there by some mechanism or that the ring itself captured gas from its surroundings. The gap between the ring and core is particularly perplexing. Detailed observations reveal very few stars in this region, far fewer than would be expected if the ring had formed from material gradually drifting outward from the core. The void is not completely empty. Faint traces of older stars can be detected, but their density is orders of magnitude lower than in either the ring or core. This suggests that something removed or prevented material from occupying the intermediate region, creating the striking separation we observe. One hypothesis involves resonance mechanisms. In disk galaxies, orbital resonances, regions where the orbital period of stars matches that of density waves or bars, can create gaps and rings by preventing material from settling into certain orbits. The Cassini division in Saturn's rings forms through a similar process, where gravitational resonances with Saturn's moons clear out particles at specific distances. Could a similar mechanism operate in Hoag's object? For this to work, the core would need to contain a rotating bar or other non-axisymmetric structure capable of generating the necessary resonances. However, observations show the core is smooth and nearly spherical, lacking the structures required for resonance-driven clearing. Another possibility involves magnetic fields. Galaxies are permeated by magnetic fields that influence the motion of ionized gas. In some scenarios, strong magnetic pressure could prevent gas from settling into certain regions, creating voids. However, the magnetic field strengths required would be enormous, far exceeding those observed in normal galaxies, and it's unclear how such fields could be generated and maintained over hundreds of millions of years. Dark matter offers yet another potential explanation. The distribution of dark matter in Hoag's object likely differs from that of normal galaxies. If the dark matter halo has an unusual density profile, perhaps with a steep drop-off at a specific radius, it could create a gravitational environment where material naturally accumulates in a ring configuration. Numerical simulations suggest that such profiles can arise in certain merger scenarios, where colliding galaxies redistribute their dark matter in non-standard ways. If Hoag's object formed through a collision, the resulting dark matter distribution might explain the ring's stability and the void separating it from the core. The ring's chemical composition provides additional clues. Spectroscopic analysis shows that the stars in the ring have metallicities, proportions of elements heavier than hydrogen and helium, similar to those of typical spiral galaxies. This indicates that the gas forming these stars had been processed through previous generations of stars, which synthesized heavy elements through nuclear fusion and dispersed them via supernova explosions. The presence of these enriched elements suggests that the ring isn't composed of pristine gas falling in from intergalactic space, but rather material that was already part of a galactic system before the ring formed. The ring's thickness is another curious feature. Observations indicate that the ring has vertical thickness, extending above and below the plane of the structure, much like the thick disks seen in spiral galaxies. This thickness implies that the stars in the ring have vertical motions in addition to their circular orbits, giving the ring a puffy, three-dimensional structure. The origin of these vertical motions is unclear. In spiral galaxies, vertical heating occurs through gravitational scattering by molecular clouds and dark matter substructures. In Hoag's object, the low density of material in the ring makes such scattering less effective, yet the ring still displays significant thickness. Collision mechanics and ring formation. The leading explanation for Hoag's object involves a galactic collision, not a head-on merger, but a precisely aimed, high-speed plunge, where a smaller galaxy passed directly through the center of a larger one. This scenario, known as a bullseye collision, can theoretically produce ring structures through a process called collisional ring galaxy formation. Understanding this mechanism requires examining the physics of galactic interactions in detail. When two galaxies collide, their stars rarely interact directly. The distances between stars are so vast that even in the densest galactic cores, the probability of stellar collisions is negligible. Instead, the primary interaction occurs between the galaxy's gas components and gravitational fields. Gas clouds in the colliding galaxies compress and shock as they pass through each other, triggering intense star formation. Meanwhile, the gravitational fields of both galaxies distort the trajectories of stars and dark matter, creating tidal forces that can reshape entire galactic structures. In a typical merger, the two galaxies approach at an angle, their disks tilting and warping as they orbit each other. The process is chaotic, with multiple close passes over hundreds of millions of years before the galaxies finally coalesce into a single remnant. During these encounters, tidal tails form long streams of stars and gas pulled out by gravitational forces. The final product is usually an elliptical galaxy, where the organized rotation of the original disks has been scrambled into random stellar orbits. A bullseye collision is different. If a smaller galaxy plunges directly through the center of a larger disk galaxy at high speed, it creates a circular shockwave that propagates outward through the disk. This shockwave compresses gas, pushing it radially outward and causing it to accumulate at a specific radius determined by the collision's energy and geometry. As the gas piles up, it cools and condenses, forming the bright ring of young stars characteristic of ring galaxies. The intruder galaxy, meanwhile, punches through and continues onward, potentially carrying away much of the original disk's material or being gravitationally disrupted in the process. Numerical simulations of bullseye collisions, first conducted in the 1970s and refined over decades with increasingly sophisticated codes, demonstrate that such impacts can indeed produce ring structures. The simulations track the motion of millions of particles representing stars, gas, and dark matter, calculating gravitational forces and hydrodynamic interactions as the collision unfolds. When the parameters are tuned correctly, intruder mass, impact velocity, disk orientation, the simulations produce rings remarkably similar to Hoag's object, circular structures of young stars surrounding an old core, separated by a gap. However, the simulations also reveal challenges. First, the collision must be nearly perfect. If the intruder passes even slightly off-center, the resulting ring becomes elliptical or lopsided. If the impact velocity is too low, the intruder doesn't fully penetrate, and the disk simply warps or forms spiral arms. If the velocity is too high, the shockwave becomes too weak to compress gas effectively, and no ring forms. The parameter space for producing a symmetric ring, like Hoag's object, is narrow, making such collisions statistically rare. Second, the intruder galaxy must be massive enough to generate a strong shockwave, but not so massive that it disrupts the entire system. Simulations suggest that the intruder should be roughly 1/10 to 1/4 the mass of the target galaxy. In Hoag's object, this implies an intruder with a mass equivalent to tens of billions of solar masses, a substantial dwarf or small spiral galaxy. Where did this intruder go? If it passed through and continued onward, it should be detectable somewhere near Hoag's object, either as a separate galaxy or as a tidal tail. Observations have not identified such a companion, suggesting the intruder may have been disrupted during the collision, its stars scattered into the halo or absorbed into the ring and core. Third, the timing must be precise. Ring galaxies are thought to be transient structures, lasting only a few 100 million to a billion years before collapsing or dispersing. The ring in Hoag's object contains young stars, indicating that star formation began relatively recently, perhaps within the last few 100 million years. This suggests we are observing Hoag's object during a brief phase of its evolution, a window of time when the ring is bright and well-defined. If the collision had occurred much earlier, the ring would have faded or spiraled inward by now. If it had occurred more recently, the ring wouldn't have had time to form stars. The fact that we see Hoag's object at this particular stage implies either remarkable timing or a longer-lived stability than simulations predict. The collision hypothesis gains support from observations of other ring galaxies. Astronomers have catalogued several dozen ring galaxies across the universe, and many show clear signs of interactions, companion galaxies nearby, tidal tails, or asymmetric structures indicating ongoing disturbances. The Cartwheel Galaxy, located 500 million light-years away in the constellation Sculptor, is a well-studied example. It displays a large outer ring, a smaller inner ring, and a disturbed core, all consistent with a recent bullseye collision. Unlike Hoag's object, the Cartwheel shows visible tidal features and a more chaotic structure, suggesting a less perfectly aligned impact or a different evolutionary stage. Comparing Hoag's object to the Cartwheel reveals important differences. The Cartwheel's ring is actively forming stars at a prodigious rate, with massive star clusters glowing intensely in ultraviolet light. The ring's expansion velocity can be measured, indicating that the collision occurred roughly 200 million years ago. The Cartwheel also has a smaller companion galaxy nearby, a likely candidate for the intruder. Hoag's object, by contrast, shows no nearby companions, and its ring appears more settled, suggesting either an older collision with the intruder long since departed or a different formation pathway altogether. Alternative collision scenarios have been proposed. Some models suggest that Hoag's object could have formed through a grazing encounter, where a companion galaxy passed close to but not directly through the disk, creating gravitational torques that pulled material outward into a ring. Others propose that the ring resulted from accretion of gas from intergalactic space, channeled into a circular orbit by the galaxy's gravitational potential. Each scenario makes testable predictions about the ring's kinematics, chemical composition, and age distribution, but current observations are not yet detailed enough to distinguish definitively between them. The core's ancient mystery. While the ring captures attention with its luminous blue stars and geometric perfection, the core of Hoag's object holds equally profound mysteries. Spectroscopic observations reveal that the core is composed predominantly of old, red stars, giants and subgiants, with ages exceeding several billion years. These stars formed when the universe was significantly younger, during an era of intense star formation activity across the cosmos. Their presence suggests that the core is a relic, a surviving remnant of a galaxy that existed long before the ring ever appeared. The core's structure resembles that of an elliptical galaxy. It is smooth, nearly spherical, and lacks the spiral arms or disk features characteristic of younger galaxies. Its stellar orbits are randomly oriented, rather than organized into a coherent rotation pattern, a hallmark of systems that have experienced violent relaxation, a process where gravitational interactions during mergers scramble stellar trajectories, erasing any memory of their original paths. This indicates that the core itself may have formed through earlier mergers, long before the event that created the ring. Measuring the core's mass presents technical challenges. Direct methods involve analyzing the velocities of stars within the core using spectroscopy. The broader the range of velocities, the stronger the gravitational pull, and hence the greater the mass. Observations show that the core contains roughly 100 billion solar masses in visible stars, comparable to the Milky Way's stellar mass. However, this visible mass alone cannot explain the ring's dynamics. The ring's rotation velocity implies a much larger total mass, upwards of several hundred billion solar masses, suggesting that the core is embedded in an extensive dark matter halo that extends far beyond the visible boundaries. The core's metallicity, the abundance of elements heavier than hydrogen and helium, provides clues about its formation history. Spectroscopic measurements indicate solar or slightly supersolar metallicity, meaning the core's stars contain as many or more heavy elements than the Sunday. This high metallicity implies that the gas from which these stars formed had been enriched by multiple generations of earlier stars, which produced heavy elements through nuclear fusion and dispersed them via supernova explosions. The enrichment process requires billions of years, consistent with the core's ancient age. Comparing the core's metallicity to that of the ring reveals a curious pattern. The ring's stars also display relatively high metallicity, though slightly lower than the cores. This suggests that the gas forming the ring originated from or was influenced by the core's material, possibly expelled during the collision that created the ring. In a bullseye collision scenario, the impacting intruder would shock gas in the target galaxy's disk, pushing it outward. If the target was the current core, the expelled gas would carry the core's chemical signature, explaining the ring's composition. However, an alternative interpretation complicates this picture. If the intruder was a gas-rich galaxy, it could have contributed its own gas to the ring formation. The ring's metallicity would then reflect a mix of material from both the target and intruder, making it difficult to disentangle their contributions. Detailed chemical abundance analyses measuring not just overall metallicity, but the ratios of specific elements like oxygen, iron, and carbon could potentially resolve this ambiguity, but such observations require large telescopes and long exposure times, and have not yet been conducted at the necessary precision for Hoag's object. The core's lack of ongoing star formation is another intriguing aspect. Unlike the ring, which blazes with young blue stars, the core shows no significant ultraviolet or far-infrared emission, indicators of recent star formation. This absence implies that the core has been quiescent for billions of years, having exhausted or expelled its gas supply long ago. In normal elliptical galaxies, quiescence typically follows major mergers, which heat or expel gas through feedback processes, supernova explosions, stellar winds, and possibly activity from a central supermassive black hole. Hoag's object almost certainly hosts a supermassive black hole at its center. As nearly all massive galaxies do, the black hole's mass can be estimated using scaling relations that connect black hole mass to the velocity dispersion of stars in the galaxy's core. For Hoag's object, these estimates suggest a black hole mass of several tens of millions of solar masses, comparable to that of the Milky Way's central black hole, Sagittarius A star. While not directly observed, this black hole likely played a role in the core's evolution, regulating star formation and possibly influencing the dynamics during the collision that formed the ring. The spatial distribution of stars within the core follows a smooth profile, with density decreasing steadily from the center outward. High-resolution imaging from Hubble Space Telescope reveals no substructure, no embedded disks, bars, or clusters that might indicate recent disturbances. This smoothness is consistent with a relaxed system, one that has had sufficient time to reach dynamical equilibrium after any violent events in its past. The relaxation timescale for a galaxy core depends on its density and size, typically ranging from hundreds of millions to a few billion years. For Hoag's object's core, this implies that any major disruptions must have occurred at least 1 billion years ago, well before the ring formed. The core's rotation presents another puzzle. While the ring displays clear rotational motion, with spectroscopic measurements showing systematic velocity gradients across its extent, the core's rotation is much weaker or possibly absent. This is typical of elliptical galaxies, where stellar orbits are oriented randomly rather than aligned in a common plane. However, if the core was once a disk galaxy that experienced a head-on collision, one might expect some residual rotation, at least in the younger stellar populations near the core's edge. The absence of such rotation suggests that either the collision was sufficiently violent to completely erase the core's angular momentum, or the core had already evolved into an elliptical-like system before the ring-forming event. The dark matter scaffold. Every visible structure in Hoag's object, the ring, the core, the gap between them, exists within a vast, invisible framework of dark matter. This dark matter halo dominates the galaxy's mass budget, providing the gravitational foundation that holds everything together. Understanding Hoag's object requires understanding this hidden scaffold, a task that pushes the limits of observational astronomy. Dark matter doesn't emit, absorb, or scatter light, making it undetectable through conventional telescopes. Its presence is inferred through gravitational effects, the motion of stars and gas, gravitational lensing of background galaxies, and the overall mass distribution needed to explain observed dynamics. In Hoag's object, the ring's rotation velocity serves as a primary probe of the underlying dark matter distribution. Measurements of the ring's rotation curve, how orbital velocity changes with distance from the core, reveal that the velocity remains roughly constant across the ring's width. In Newtonian gravity, this flat rotation curve implies that mass continues to increase linearly with radius, even beyond the visible edge of the ring. Since visible matter, stars and gas, is concentrated in the ring and core, the additional mass must come from dark matter extending far into the galaxy's outer regions. Modeling the dark matter halo requires making assumptions about its density profile, how dark matter density changes with distance from the center. The most commonly used profile is the Navarro-Frenk-White (NFW) profile, derived from cosmological simulations of structure formation. The NFW profile predicts that dark matter density is highest near the galactic center and decreases as a power law with increasing radius. For Hoag's object, fitting an NFW profile to the rotation curve suggests a total dark matter mass of several hundred billion to a trillion solar masses, extending out to hundreds of thousands of light-years far beyond the visible ring. However, the NFW profile is not the only possibility. Alternative profiles, such as the Inasto profile or chord profiles with constant central density, can also fit the data, often with comparable accuracy. Distinguishing between these models requires observations at both the innermost regions, probing the core's velocity dispersion, and the outermost regions, where satellite galaxies or globular clusters could trace the halo's extent. For Hoag's object, such detailed observations are lacking, leaving the precise dark matter distribution uncertain. The collision that likely formed Hoag's object would have profoundly affected the dark matter distribution. During a bullseye collision, the dark matter halos of the colliding galaxies interpenetrate without significant interaction, since dark matter particles pass through each other without colliding. However, the gravitational perturbation caused by the collision redistributes dark matter, potentially creating asymmetries, overdensities, or even secondary halos. Simulations show that after such collisions, the dark matter halo can become elongated or develop substructure, with clumps of dark matter trailing behind the visible components. One intriguing possibility is that the gap between the ring and core is actually filled with dark matter, even though it contains few visible stars. If the collision displaced baryonic matter, normal matter, outward, while leaving dark matter largely undisturbed, the gap could represent a region dominated by dark matter's gravitational influence. This dark matter would hold the ring in its circular orbit, preventing it from spiraling inward or dispersing outward. Observations of the gap's gravitational potential, perhaps through weak gravitational lensing of distant background galaxies, could test this hypothesis. But such measurements are extremely challenging, given Hoag's object's distance and size. Gravitational lensing provides an independent method to probe dark matter in Hoag's object. If a background galaxy happens to lie nearly along our line of sight to Hoag's object, its light would be bent by the foreground galaxy's gravity, creating distorted images or arcs. By analyzing these distortions, astronomers can reconstruct the mass distribution of the lensing galaxy, including its dark matter component. Remarkably, Hubble images of Hoag's object reveal a small background galaxy visible through the gap between the ring and core. While this galaxy is not sufficiently distorted to provide strong lensing constraints, it does offer a potential target for future high-resolution observations that could map Hoag's object's dark matter distribution in unprecedented detail. Another technique involves studying the motions of satellite galaxies or globular clusters orbiting Hoag's object. Just as the moons of Jupiter reveal Jupiter's mass through their orbital periods, any companions orbiting Hoag's object would trace the gravitational pull of both visible and dark matter. However, no confirmed satellites have been detected around Hoag's object, likely because it resides in a relatively isolated region of space, far from the dense environments where satellite galaxies are common. This isolation itself is noteworthy. It suggests that Hoag's object has experienced relatively few subsequent interactions since the collision that formed the ring, allowing the structure to persist without disruption. The dark matter halo also influences the ring's stability over time. Simulations show that without a sufficiently massive halo, ring structures are unstable and quickly collapse or fragment into spiral arms. The halo's gravitational potential acts like a containing wall, maintaining the ring's circular geometry despite perturbations from internal density variations or external gravitational influences. The nearly perfect circular shape of Hoag's object's ring thus provides indirect evidence for a smooth, axisymmetric dark matter halo, one that has not been significantly disturbed by recent interactions. The gas dynamics puzzle. Gas plays a critical role in Hoag's object's story, both in the ring's current star formation and in the collision that likely created the structure. Understanding how gas behaves during galactic collisions and how it flows within the ring provides essential clues to the object's formation and evolution. Radio observations of neutral hydrogen, Hi, reveal significant gas reservoirs in Hoag's object, concentrated almost entirely in the ring. The total Hi mass is estimated at several billion solar masses, sufficient to sustain star formation for hundreds of millions of years at the current rate. This gas exhibits ordered rotation, with velocities reaching several hundred kilometers per second, consistent with the stellar rotation curve measured spectroscopically. The gas's distribution within the ring is not uniform. High-resolution radio maps show clumps and filaments, indicating that the gas has fragmented into discrete clouds rather than forming a smooth, continuous disk. This clumpiness is expected in star-forming regions, where gravitational instabilities cause gas to collapse into dense molecular clouds that subsequently form stars. The observed clump masses range from millions to tens of millions of solar masses, comparable to giant molecular clouds in spiral galaxies like the Milky Way. The origin of this gas is central to understanding the ring's formation. In the bullseye collision scenario, gas from the target galaxy's disk would be shock-heated and pushed outward by the impacting intruder. As the shockwave propagates, gas accumulates at a characteristic radius determined by the collision's energy and the galaxy's gravitational potential. This accumulated gas cools over tens to hundreds of millions of years, eventually collapsing to form stars, the young, blue stars now visible in the ring. However, shock heating raises a problem. When gas is compressed in a shock, its temperature increases dramatically, often reaching millions of degrees. At such high temperatures, gas pressure opposes gravitational collapse, preventing star formation until the gas cools sufficiently. The cooling timescale depends on the gas density and the efficiency of radiative processes that carry away thermal energy. In low-density regions, cooling can take billions of years. In dense molecular clouds, it occurs much faster, within a few million years. For Hoag's object's ring, the presence of young stars indicates that cooling has been efficient enough to allow star formation to proceed. This implies that the gas density in the ring exceeds a critical threshold, or that additional mechanisms such as magnetic fields or turbulence have aided cooling. Observations of molecular gas, particularly carbon monoxide, AO, emission, would help constrain the gas density and temperature, but such observations are challenging due to Hoag's object's distance and the faintness of molecular emission. Another puzzle involves the gas's angular momentum. In a disk galaxy, gas orbits in roughly circular paths, maintaining angular momentum as it slowly migrates inward, fueling star formation throughout the disk. In Hoag's object, the gas is confined to a narrow ring, suggesting that angular momentum is highly conserved, perhaps more so than in typical galaxies. This conservation could result from the collision's geometry, which deposited gas into orbits with similar angular momentum, or from the dark matter halo's gravitational potential, which preferentially supports circular orbits at a specific radius. The ring's gas also exhibits vertical motion, extending above and below the plane of the ring. Spectroscopic observations reveal velocity components perpendicular to the ring's rotation, indicating that gas is not confined to a thin disk but has significant thickness. This vertical motion could originate from supernova explosions, which inject energy and momentum into the surrounding gas, driving outflows and creating turbulence. Alternatively, the collision itself might have imparted vertical velocities to the gas, which persist over time due to the low damping rate in the diffuse halo regions above and below the ring. Comparing the gas distribution to the stellar distribution reveals subtle differences. While both gas and stars are concentrated in the ring, the gas extends slightly farther outward and inward than the stars, suggesting ongoing accretion and redistribution. This could indicate that gas is still settling into equilibrium after the collision, or that tidal interactions with the core or dark matter halo are continuously perturbing the gas's orbit. The absence of significant gas in the core is also telling. Elliptical galaxies typically contain little cold gas, as their formation through mergers heats or expels gas, shutting down star formation. Hoag's object's core fits this pattern, suggesting it underwent a transformative event, possibly the same collision that formed the ring that removed or exhausted its gas supply. If gas was present in the core before the collision, the impacting intruder could have stripped it away, driving it outward into the ring. Alternatively, Feedback processes from supernovae or the central black hole could have ejected gas from the core, preventing it from forming new stars. Star formation in the ring. The ring of Hoag's object is a stellar nursery, actively forming stars at a modest but steady rate. Observations in ultraviolet and blue wavelengths reveal bright clusters of young stars scattered throughout the ring, with ages ranging from a few million to a few 100 million years. These stars are predominantly massive, short-lived O and B-type stars that emit intense ultraviolet radiation, ionizing surrounding gas and creating glowing H2 regions, clouds of ionized hydrogen that mark sites of recent star formation. The total star formation rate in the ring is estimated at roughly 1 solar mass per year, based on ultraviolet luminosity and hydrogen alpha emission measurements. This rate is significantly lower than that of starburst galaxies, which can form hundreds of solar masses per year, but comparable to normal spiral galaxies like the Milky Way. Given the ring's gas reservoir of several billion solar masses, star formation could continue at the current rate for hundreds of millions of years before the gas is exhausted. Star formation in Hoag's object's ring follows the same physical processes as in other galaxies. Gas clouds collapse under gravity when their mass exceeds the Jeans mass, the critical mass above which gravitational forces overcome internal gas pressure. In the ring, the Jeans mass depends on the gas temperature and density, both of which vary with position. Denser regions form stars more readily, while lower density regions remain quiescent until perturbations, such as supernova shock waves or spiral density waves, trigger collapse. However, the ring's geometry introduces unique factors. Unlike a disk galaxy, where spiral arms can trigger coordinated star formation by compressing gas as they rotate through the disk, Hoag's object's ring lacks such structures. Instead, star formation appears more stochastic, driven by local instabilities rather than large-scale patterns. This could result from the ring's relatively narrow width, which limits the development of large-scale density waves, or from the absence of a central bar, which in barred spirals drives gas inward and regulates star formation. The stellar initial mass function, IMF, the distribution of stellar masses at birth, provides insights into star formation conditions. In most galaxies, the IMF is universal, with many low-mass stars and few high-mass stars following a power law known as the Salpeter IMF. Observations of Hoag's object's ring are consistent with a standard IMF, suggesting that despite the unusual galactic structure, star formation proceeds normally once gas clouds collapse. The spatial distribution of young stars within the ring shows clustering, with distinct star-forming regions separated by relatively empty stretches. This clumpiness indicates that star formation is patchy, concentrated in regions where gas density is highest. These clusters likely formed from individual giant molecular clouds, each containing millions of solar masses of gas. Over time, as massive stars in these clusters explode as supernovae, they disperse the remaining gas, quenching further star formation in that region. New star formation then shifts to other parts of the ring where gas remains undisturbed. The ring's kinematics influence star formation efficiency. In regions where gas orbits faster or slower than the average, shear forces can compress gas, triggering collapse. Conversely, strong shear can also disrupt clouds before they collapse, preventing star formation. Observations of velocity gradients within the ring suggest that shear is relatively weak, consistent with the ring's circular geometry and smooth rotation curve. This weak shear may actually favor star formation by allowing clouds to remain intact long enough to collapse. Feedback from massive stars regulates star formation over longer timescales. When O and B-type stars explode as supernovae, they inject enormous amounts of energy into the surrounding gas, heating it and driving outflows. These outflows can compress nearby gas, triggering new waves of star formation, a process called triggered star formation, or they can disperse gas entirely, suppressing further star formation. In Hoag's object, the balance between these effects determines the ring's long-term evolution. If feedback is too strong, star formation will cease prematurely. If too weak, star formation will continue until all gas is consumed. The ring's metallicity gradient, if present, would provide clues about gas mixing and star formation history. In spiral galaxies, metallicity typically decreases with distance from the center, reflecting inside-out galaxy formation, where inner regions form stars earlier and become more chemically enriched. In Hoag's object, The ring's narrow extent makes gradients difficult to detect, but future spectroscopic surveys could reveal subtle variations that trace gas flows and mixing processes. The search for companions. In the bullseye collision scenario, an intruder galaxy punched through Hoag's object, creating the ring. But where is the intruder now? If it survived the encounter, it should be detectable somewhere near Hoag's object, either as a separate galaxy moving away from the collision site or as a disrupted remnant orbiting nearby. Extensive searches have been conducted to identify such a companion, but the results remain inconclusive. Deep imaging surveys have examined the region surrounding Hoag's object, looking for faint galaxies that could be the intruder. These searches cover a radius of several 100,000 light-years, sufficient to detect any substantial companion galaxy. A few small galaxies appear in the field, but spectroscopic measurements show they are either much closer or much farther away than Hoag's object, lying along the line of sight by coincidence rather than being physically associated. The absence of a detectable intruder raises several possibilities. First, the intruder may have been significantly disrupted during the collision, its stars scattered into an extended halo that is too diffuse to detect against the sky background. Simulations show that in high-velocity collisions, the intruder can be tidally shredded by the target galaxy's gravity, leaving only faint streams of stars that fade below detection thresholds within a few 100 million years. Second, the intruder may have already moved far from Hoag's object, carried away by its original momentum. If the collision occurred several 100 million years ago and the intruder was traveling at several 100 kilometers per second, it could now be hundreds of thousands of light-years away, far enough that it no longer appears associated with Hoag's object in surveys covering limited sky areas. Third, the intruder might never have been a luminous galaxy. Some models propose that Hoag's object's ring formed through interaction with a massive dark matter halo or a gas-rich but star-poor dwarf galaxy. Such an intruder would have provided the necessary gravitational perturbation to create the ring without leaving a bright stellar signature. However, this scenario faces challenges. Low luminosity dwarfs typically lack sufficient mass to generate the energetic shock waves required to form such a large, well-defined ring. Tidal features, long streams of stars pulled out by gravitational interactions, are often associated with galactic collisions. These features are key diagnostics of past interactions, revealing the geometry and timescale of the encounter. In Hoag's object, no prominent tidal tails or streams have been detected in deep optical or infrared images. This absence suggests either that the collision was relatively clean, with minimal tidal disruption, or that any tidal features have faded below detection limits as stars disperse over time. However, ultra-deep imaging with next-generation telescopes could reveal faint tidal features currently invisible. Projects like the James Webb Space Telescope's JWST, deep field observations and future ground-based telescopes, equipped with adaptive optics, will push surface brightness sensitivity to unprecedented levels, potentially uncovering ghostly streams or shells around Hoag's object that hold clues to its violent past. Another approach involves searching for kinematic signatures of the intruder. If some of the intruder's stars were captured into Hoag's object's halo, they would retain distinct velocity patterns, orbiting with different angular momentum than the native stars. Spectroscopic surveys measuring velocities of individual stars in Hoag's object's halo could identify such populations, but this requires resolving individual stars at 600 million light-years, a formidable challenge even for the largest telescopes. Globular clusters associated with the intruder could also betray its presence. Globular clusters are ancient, gravitationally bound groups of stars that orbit galaxies. When galaxies merge, their globular cluster systems mix. If the intruder contributed globular clusters to Hoag's object, these clusters might have distinct properties, colors, metallicities, or spatial distributions that distinguish them from clusters native to the target galaxy. Surveys of Hoag's object's globular cluster system have been limited by the galaxy's distance, but future observations could provide critical constraints. Why ring galaxies are so rare? If bullseye collisions can produce ring galaxies like Hoag's object, why do we see so few of them? In a universe containing hundreds of billions of galaxies, collisions are common. Surveys reveal that a significant fraction of galaxies show signs of interactions, warped disks, tidal tails, disturbed morphologies, yet ring galaxies represent less than 1/10 of 1% of all observed galaxies. This rarity demands explanation. The primary reason is geometric. A bullseye collision requires the intruder galaxy to pass almost directly through the target's center. In three-dimensional space, this alignment is statistically unlikely. Most collisions occur at oblique angles, where the intruder's trajectory misses the target's center by tens of thousands of light-years. Such off-center collisions produce different outcomes: tidal tails, warped disks, or spiral arms, but not symmetric rings. Only a small fraction of collisions satisfy the geometric constraints for ring formation. Quantitative estimates suggest that bullseye collisions account for less than 1% of all galactic interactions. Even within this subset, not all produce observable rings. The intruder's mass, the target's gas content, and the collision velocity must all fall within specific ranges. Too massive, an intruder disrupts the target entirely. Too light, and the shockwave is insufficient to create a ring. If the target lacks gas, no star formation occurs to make the ring visible. If the collision velocity is too low, the intruder doesn't penetrate cleanly. Too high, and the shockwave becomes too weak. Timing also contributes to ring galaxies' rarity. Even when a collision produces a ring, the structure is transient. Simulations predict that rings persist for several 100 million years to 1 billion years before collapsing back onto the core or dispersing into the halo. This timescale is short compared to the age of the universe, less than 10% of cosmic history. Observing a galaxy during this brief phase is like catching a firefly's flash. Possible but requiring good timing, the vast majority of past ring galaxies have already faded, their structures erased by subsequent evolution. Environmental factors influence ring galaxy formation rates. In dense galaxy clusters, high-velocity encounters are common, but the collision speeds are often too high for ring formation. In isolated regions, velocities are lower, but encounters are infrequent. Ring galaxies seem to occur most often in intermediate density environments, groups, or the outskirts of clusters where collision rates and velocities strike the right balance. Selection effects also play a role. Ring galaxies are easier to identify when the ring is bright and the geometry is edge-on or face-on. At intermediate inclinations, the ring and core can overlap in projection, making the structure ambiguous and leading observers to misclassify the galaxy as a peculiar spiral or interacting system. Surveys designed to find ring galaxies use automated algorithms to detect circular structures, but these algorithms can miss rings with low surface brightness or complex morphologies. Despite their rarity, ring galaxies are invaluable laboratories for studying galactic dynamics, star formation, and dark matter. Their simple, symmetric structures allow astronomers to model their formation with greater confidence than more chaotic mergers. Each ring galaxy discovered adds to the sample, improving statistics and enabling comparative studies that reveal underlying physical principles. Recent large area surveys, such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have identified dozens of new ring galaxy candidates. Follow-up observations confirm that some are bona fide ring galaxies, while others are chance alignments or artifacts. As surveys push to greater depths and wider areas, the census of ring galaxies will grow, providing a richer dataset for understanding their formation and evolution. Hoag's object remains the archetype, the most perfectly formed ring galaxy known. Its symmetry and isolation make it the ideal target for detailed studies. Every new observation refines our understanding, not just of Hoag's object itself, but of the broader processes that sculpt galaxies across cosmic time: gravitational lensing and hidden mass. One of the most serendipitous discoveries in Hoag's object images is the presence of a background galaxy visible through the gap between the ring and core. This background galaxy, located roughly 1 billion light-years beyond Hoag's object, appears as a small, reddish smudge in Hubble images. Its position, almost perfectly aligned behind the gap, provides a rare opportunity to study Hoag's object's gravitational influence through weak gravitational lensing. Gravitational lensing occurs when a massive foreground object bends the light from a more distant background source. The amount of bending depends on the foreground object's mass and the geometry of the alignment. In strong lensing, the distortion is dramatic, producing multiple images or Einstein rings. In weak lensing, the distortion is subtle, causing slight stretching or shearing of the background object's shape. Measuring these distortions allows astronomers to infer the foreground object's total mass, including dark matter, For Hoag's object, the background galaxy's light passes through regions dominated by dark matter in the gap between the ring and core. If dark matter is concentrated in the gap, it would enhance the lensing effect, causing additional distortion. Conversely, if the gap is relatively empty of mass, the lensing would be weaker. By carefully analyzing the background galaxy's shape and brightness, astronomers can constrain the mass distribution in the gap. However, weak lensing measurements are challenging. The background galaxy is faint and small, requiring high-resolution imaging to resolve its structure. Moreover, intrinsic asymmetries in the background galaxy's shape unrelated to lensing can mimic or obscure lensing distortions. Disentangling intrinsic shape from lensing effects requires statistical analysis of many background galaxies, but in Hoag's object's case, only one background galaxy is conveniently located. This limits the precision of lensing constraints. Despite these challenges, preliminary analyses suggest that the lensing effect is consistent with expectations from models where the gap contains a smooth dark matter distribution. This supports the hypothesis that dark matter fills the gap, maintaining the ring's orbit even though visible stars are sparse. Future observations with larger telescopes, such as the James Webb Space Telescope or the next-generation extremely large telescope, could resolve the background galaxy in greater detail, providing tighter constraints on Hoag's object's mass distribution. Gravitational lensing also offers a way to search for dark matter substructure within Hoag's object. Cosmological simulations predict that dark matter halos contain numerous subhalos, clumps of dark matter ranging from millions to billions of solar masses. These subhalos can perturb the paths of light rays passing through the halo, creating small-scale variations in the lensing signal. Detecting these perturbations would confirm the existence of subhalos and provide insights into dark matter's nature on small scales. In principle, microlensing the transient brightening of a background star when a foreground dark matter clump passes in front of it could also probe Hoag's object's dark matter. However, the vast distance to Hoag's object makes individual stars in the background galaxy unresolvable, rendering microlensing impractical with current technology. Another lensing-related phenomenon is time delay. If the background galaxy varied in brightness, for example, due to a supernova or active galactic nucleus light traveling different paths through Hoag's object's gravitational field would arrive at Earth at different times, separated by days to months. Monitoring the background galaxy for variability could reveal such time delays, providing an independent measure of Hoag's object's mass. However, this requires long-term, high-cadence observations which have not yet been conducted. The background galaxy itself is an interesting object. Its redshift indicates it lies at a distance corresponding to when the universe was roughly 10 billion years old, during the peak era of cosmic star formation. Studying this galaxy, even as a secondary target, provides a window into galaxy evolution at a critical epoch. Its position behind Hoag's object is purely coincidental, but it transforms Hoag's object into a natural laboratory for studying both the foreground and background systems simultaneously. The role of dark energy. While dark matter dominates Hoag's object's mass, another mysterious component, dark energy, shapes the universe's large-scale structure and evolution. Dark energy drives the accelerated expansion of the universe, a discovery recognized by the 2011 Nobel Prize in Physics. Though dark energy's influence on individual galaxies is negligible, understanding Hoag's object's place in the cosmos requires considering dark energy's role in the universe's overall dynamics. Dark energy constitutes roughly 70% of the universe's total energy density. Unlike matter, which clusters under gravity, dark energy exerts a repulsive effect, causing space itself to expand at an accelerating rate. This expansion affects the universe's large-scale structure, determining the rate at which galaxies form, merge, and evolve over cosmic time. For Hoag's object, dark energy's impact is indirect. The collision that formed the ring occurred hundreds of millions of years ago, when the universe was slightly smaller and denser than today. The probability of galactic collisions was higher then, as galaxies were closer together on average. As the universe expands and galaxies drift apart, collision rates decrease. In the far future, billions of years from now, galaxies beyond the local group will be carried away by cosmic expansion faster than gravity can pull them together, rendering collisions increasingly rare. This implies that ring galaxies like Hoag's object are more common in the past than they will be in the future. Observing distant galaxies looking back in time due to light's finite speed should reveal higher fractions of interacting and ring galaxies, a prediction supported by deep field surveys. The Hubble Ultra Deep Field and other surveys show that galaxies at high redshifts, distant epochs, exhibit more disturbed morphologies and higher interaction rates than nearby galaxies, consistent with a universe where collisions were more frequent. Dark energy also affects the universe's age and size. By accelerating expansion, dark energy reduces the time available for structure formation compared to a universe without dark energy. This influences the number and types of galaxies we observe today. In a universe dominated by matter alone, expansion would decelerate, allowing more time for galaxies to merge and evolve. Dark energy cuts this process short, freezing the universe's structure into its current configuration. The cosmological constant, the simplest model of dark energy, remains constant over time, exerting a steady repulsive pressure. Alternative models, such as dynamical dark energy, predict that dark energy's strength changes with cosmic epoch, potentially growing stronger or weaker. Testing these models requires precise measurements of the universe's expansion history, achieved through observations of distant supernovae, cosmic microwave background anisotropies, and large-scale galaxy distributions. Hoag's object contributes to these cosmological studies indirectly. By providing a well-defined system for studying galactic dynamics and mass distribution, it helps calibrate models of galaxy formation that feed into larger cosmological frameworks. Understanding how galaxies like Hoag's object form and evolve under the influence of dark matter and dark energy improves our ability to interpret observations of the distant universe where such processes are observed in action. Moreover, the rarity of ring galaxies provides a statistical constraint on collision rates and galaxy encounter dynamics, which in turn constrain the density and clustering of matter in the universe. If ring galaxies were far more or less common than observed, it would indicate discrepancies in our understanding of structure formation, potentially requiring revisions to cosmological models. Comparisons to other ring galaxies. Hoag's object is the most famous ring galaxy, but it is not alone. Astronomers have catalogued several dozen ring galaxies, each with unique properties that illuminate different aspects of ring formation and evolution. Comparing Hoag's object to these other systems reveals both universal principles and individual peculiarities. The Cartwheel Galaxy, located in the constellation Sculptor, is the most intensively studied ring galaxy. Unlike Hoag's object, the Cartwheel displays a chaotic structure with two distinct rings, an inner ring and an outer ring, along with spokes of blue stars connecting them to the core. The outer ring is expanding outward at roughly 90 kilometers per second, a remnant of the shockwave generated by a recent collision. The Cartwheel's ring is much larger than Hoag's, spanning 150,000 light-years, and far more active, forming stars at rates exceeding 10 solar masses per year. The Cartwheel's asymmetry and multiple rings suggest a more complex collision history than Hoag's object. Simulations indicate that the Cartwheel's structure resulted from an off-center collision, where the intruder passed slightly to one side of the target's core. This geometry produced two expanding rings, rather than a single, symmetric structure. The presence of a nearby companion galaxy, likely the intruder, supports this interpretation. The Cartwheel, therefore, represents an earlier evolutionary stage, or a different collision geometry compared to Hoag's object. AM 064 4-741, another ring galaxy in the southern sky, resembles Hoag's object more closely. It features a single, symmetric ring surrounding a yellow core, with a prominent gap separating the two components. Like Hoag's object, AM 0644-741 lacks a visible companion, suggesting the intruder has either dispersed or moved far away. However, AM 0644-741's ring contains more molecular gas and forms stars at a higher rate, indicating a younger system where the collision occurred more recently. The Lindsay-Shapley ring, also known as AM 0644-741's companion, is a peculiar system where the ring appears detached from any central core. This extreme configuration suggests that the collision was so energetic that the core was entirely disrupted, leaving only the ring as a remnant. Alternatively, the core may be present but heavily obscured by dust, rendering it invisible in optical wavelengths. Infrared observations could resolve this ambiguity. Polar ring galaxies represent a related but distinct category. In these systems, a ring of stars and gas orbits perpendicular to the main galactic disk, rather than in the same plane. Polar rings likely form through the accretion of material from a companion galaxy that approached at a steep angle. Though geometrically different from Hoag's object, polar ring galaxies share the common feature of material orbiting at large radii in well-defined structures, held together by gravitational forces. Comparative studies of ring galaxies reveal common trends. Most ring galaxies display young, blue stars in their rings, indicating recent star formation triggered by collisions. The rings' sizes vary widely, from tens of thousands to hundreds of thousands of light-years, depending on the collision's energy and the target galaxy's properties. Star formation rates correlate with ring brightness, with more luminous rings forming stars more rapidly. The presence or absence of companions, tidal tails, and additional structures reflects the collision's geometry and timescale. Statistical analyses of ring galaxy samples provide insights into their lifetimes and evolutionary pathways. By comparing the number of ring galaxies observed at different distances, and thus different cosmic epochs, astronomers estimate that ring structures persist for several 100 million years before fading. This timescale is consistent with simulations and supports the interpretation that ring galaxies are transient phases in galactic evolution. Hoag's object stands out within this sample for its exceptional symmetry and the absence of a detectable companion. These features make it either an unusually old ring galaxy, where the intruder has long since vanished and the structure has settled into equilibrium, or an exceptionally clean collision, where minimal disruption preserved geometric perfection. Either interpretation underscores Hoag's object's uniqueness and its value as a benchmark for theoretical models, future observations, and unanswered questions. Despite decades of study, Hoag's object retains many mysteries. Future observations promise to address some of these. Leveraging advances in telescope technology, detector sensitivity, and computational modeling, several key questions remain unanswered, each requiring targeted observational strategies. First, the precise mass distribution within Hoag's object remains uncertain. While rotation curve measurements constrain the total mass, the relative contributions of stars, gas, and dark matter in the ring, gap, and core are poorly known. Detailed spectroscopic surveys, measuring velocities of stars at multiple positions across the galaxy, would map the gravitational potential with higher precision. Such surveys require large telescopes equipped with multi-object spectrographs capable of capturing spectra from hundreds of stars simultaneously. Second, the chemical abundance patterns in the ring and core need clarification. Current metallicity estimates are based on integrated light spectra which average over many stars. Resolving individual stars or star clusters would allow differential chemical analysis, revealing variations in element ratios that trace the ring's formation history. The James Webb Space Telescope's infrared capabilities make it ideally suited for this task, as it can resolve individual star clusters in distant galaxies and measure their spectra with high precision. Third, the intruder galaxy's fate remains unknown. Deep imaging surveys targeting the region surrounding Hoag's object could reveal faint tidal streams or dispersed stellar halos that betray the intruder's presence. Ultra-deep exposures using next-generation telescopes, such as the Vera-C, Rubin Observatory's legacy survey of space and time, will push surface brightness limits to unprecedented levels, potentially uncovering features invisible to current instruments. Fourth, the dark matter distribution in the gap between ring and core requires direct probing. Weak gravitational lensing of the background galaxy offers one avenue, but requires higher resolution imaging than currently available. Alternatively, detecting gravitational microlensing events, transient brightenings caused by dark matter clumps passing in front of background stars, would provide direct evidence for dark matter substructure, though this demands long-term monitoring campaigns. Fifth, the ring's long-term stability and evolution are uncertain. Simulations predict that rings eventually collapse or disperse, but the timescale depends on factors like the dark matter halo's density profile and external perturbations from nearby galaxies. Monitoring Hoag's object over decades to centuries, admittedly impractical for human observers, would reveal whether the ring is static or slowly evolving. Alternatively, comparing Hoag's object to ring galaxies at different evolutionary stages could constrain evolutionary timescales statistically. Sixth, The role of the central supermassive black hole remains unexplored. Though the core appears quiescent, lacking signs of active accretion, the black hole's mass and influence on the surrounding stars and gas are unknown. Radio and X-ray observations targeting the core could detect faint emission from the black hole, constraining its mass and accretion rate. Variability monitoring might reveal low-level activity, providing insights into the black hole's feeding history. Seventh, the ring's magnetic field structure is completely unmapped. Magnetic fields regulate star formation and influence gas dynamics, but measuring them in distant galaxies is challenging. Polarimetry observations, which detect the alignment of starlight or radio emission caused by magnetic fields, could map the field strength and geometry within the ring. Such observations are feasible with radio interferometers, like the Atacama Large Millimeter Array and the Square Kilometer Array. Eighth, the three-dimensional structure of the ring requires confirmation. Current observations assume the ring is circular and nearly face-on, but inclination effects could distort this interpretation. Kinematic modeling, combining rotation curves with velocity dispersion measurements, would constrain the ring's inclination and thickness, providing a complete geometric picture. Finally, the broader context of Hoag's object within the cosmic web remains unexplored. Is Hoag's object part of a larger galaxy group or supercluster? Are there environmental factors that influenced its formation or evolution? Widefield surveys mapping galaxy distributions around Hoag's object would place it in cosmological context, revealing whether its isolation is typical or exceptional. The broader implications for galaxy evolution. Hoag's object is more than an astronomical curiosity. It is a laboratory for testing theories of galaxy formation and evolution. Its existence challenges simplified models and forces astronomers to consider processes that are rare but physically plausible. Understanding Hoag's object has broader implications for how we interpret galaxy diversity and the mechanisms driving galactic change across cosmic history. One major implication concerns collision dynamics. Most models of galaxy evolution treat collisions as chaotic events that disrupt structure and trigger starbursts. Hoag's object demonstrates that under specific conditions, collisions can produce highly ordered structures. This suggests that the outcomes of galactic interactions are more diverse than previously appreciated, with the potential for creating a wider range of morphologies than the traditional classification schemes allow. Another implication involves dark matter's role in shaping visible structures. The ring's stability requires a specific dark matter distribution, one that provides enough gravitational support to maintain circular orbits without allowing the ring to collapse inward. This highlights dark matter's active role in determining galactic morphology, not merely as an invisible scaffold, but as a dynamic component that influences gas flows, stellar orbits, and structural evolution. Hoag's object also informs our understanding of star formation regulation. The ring's modest star formation rate, sustained over hundreds of millions of years, indicates efficient conversion of gas into stars without rapid exhaustion. This efficiency depends on factors like gas density, cooling rates, and feedback from supernovae processes that operate universally but manifest differently depending on galactic structure. Studying star formation in such an unusual environment tests whether our models, developed primarily from spiral and elliptical galaxies, apply broadly or require modification for exotic systems. The rarity of ring galaxies constrains the parameter space for galactic collisions. By counting ring galaxies and estimating their lifetimes, astronomers can infer collision rates and geometries across cosmic time. These constraints feed into hierarchical models of structure formation, where galaxies grow through mergers and accretion. If collision rates differ from predictions, it signals gaps in our understanding of galaxy clustering, dynamics, or dark matter's influence on large-scale structure. Hoag's object also serves as a test case for numerical simulations. Simulating galaxy collisions requires solving the equations of gravity and hydrodynamics for billions of particles, a computationally intensive task. Comparing simulations to real galaxies like Hoag's object validates or refutes the physical assumptions embedded in the codes. Discrepancies between observed and simulated properties highlight areas needing refinement, driving improvements in computational models. Furthermore, Hoag's object illustrates the importance of transient phases in galaxy evolution. Galaxies spend most of their lives in stable configurations, spirals quietly, forming stars, ellipticals aging passively. But transient events, like collisions, can dramatically alter their trajectories. even if the resulting structures persist for only a fraction of cosmic history. Recognizing and studying these transient phases is essential for reconstructing the full evolutionary pathways that galaxies traverse. The object also raises questions about the diversity of galactic environments. Most galaxies reside in groups or clusters where interactions are frequent. Hoag's object appears relatively isolated, suggesting that ring galaxies may preferentially form in lower density environments where collision velocities are moderate and subsequent interactions rare. This environmental dependence implies that galaxy morphology is shaped not only by internal processes, but also by the surrounding cosmic landscape. Finally, Hoag's object reminds astronomers of the universe's capacity for surprise. Despite centuries of observation and decades of sophisticated modeling, galaxies continue to reveal structures and behaviors that defy expectations. Hoag's object is a testament to the richness of the cosmos and the necessity of maintaining open-minded, empirical approaches to understanding it. The symmetry problem. Returning to Hoag's object's most striking feature, its near-perfect symmetry, we confront a fundamental tension. Symmetry in nature often reflects underlying conservation laws or equilibrium states. A spinning sphere remains symmetric because angular momentum is conserved. A soap bubble is round because surface tension minimizes energy. But galaxies are messy, dynamic systems subject to countless perturbations. How does Hoag's object maintain its geometric perfection? Simulations of bullseye collisions produce rings, but rarely with Hoag's object's level of symmetry. Most simulated rings display asymmetries, lopsided structures, or multiple rings features seen in galaxies like the cartwheel. Achieving perfect symmetry requires fine-tuning. The intruder must pass precisely through the target's center with exactly the right velocity and mass. Even slight deviations produce observable asymmetries. One possibility is observational bias. Hoag's object's symmetry may be an illusion arising from its orientation. If the ring is slightly inclined to our line of sight, projection effects could mask intrinsic asymmetries, making the structure appear more symmetric than it truly is. High-resolution kinematic modeling, which reconstructs three-dimensional structure from velocity measurements, could test this hypothesis. But current data lacks sufficient precision. Alternatively, the symmetry might reflect unusually smooth initial conditions. If the target galaxy had a smooth, axisymmetric dark matter halo and gas distribution before the collision, the resulting ring would naturally inherit this symmetry. Most galaxies, however, have lumpy dark matter halos and asymmetric gas distributions due to past interactions and accretion events. Hoag's object might be rare because its progenitor was unusually pristine, an isolated galaxy that had not experienced recent disturbances before the collision. Another factor is time. Over hundreds of millions of years, gravitational interactions smooth out small-scale asymmetries through a process called violent relaxation. Stars exchange energy and angular momentum during close encounters, redistributing themselves into more symmetric configurations. If Hoag's object is older than most ring galaxies, this smoothing process may have erased initial asymmetries, producing the observed perfection. However, violent relaxation has limits. It cannot erase large-scale asymmetries caused by ongoing perturbations, such as gravitational interactions with nearby galaxies or internal instabilities. Hoag's object's isolation may be key. With few nearby companions, external perturbations are minimized, allowing the ring to maintain symmetry over time. The ring's rotation also contributes to stability. Rotating systems resist deformation through centrifugal effects. A rotating ring, like a spinning hoop, maintains its shape against gravitational forces trying to collapse it. Hoag's object's rotation velocity is substantial, several hundred kilometers per second, providing significant centrifugal support. Yet the symmetry problem extends beyond shape. The ring's star formation is remarkably uniform, with no dominant star-forming regions or azimuthal variations. This uniformity suggests that gas is distributed evenly around the ring, without clumping or fragmentation into discrete clouds. Normally, gravitational instabilities would cause gas to fragment, creating localized star-forming regions. Hoag's object's uniform star formation implies that either instabilities are suppressed or that gas replenishes quickly enough to maintain smooth distribution. Magnetic fields could play a role. Strong, ordered magnetic fields can suppress instabilities by providing additional pressure support, smoothing out density fluctuations, If Hoag's object's ring contains strong magnetic fields aligned with the ring's geometry, they could maintain uniform gas distribution and star formation. However, magnetic field measurements are lacking, leaving this hypothesis untested. Why Hoag's object matters. Hoag's object occupies a unique position in astronomy, a single galaxy that defies easy explanation and challenges our understanding of galactic physics. Its importance extends beyond its individual properties to what it represents: the universe's ability to create structures that push the boundaries of theoretical models. Studying Hoag's object teaches us humility. Despite tremendous advances in observational technology and computational power, we still struggle to fully explain this one galaxy. Its symmetry, its ring, its missing companion all point to gaps in our knowledge. These gaps are not failures, they are opportunities. Every unexplained feature of Hoag's object is a question waiting for an answer, a puzzle inviting solution. The object also demonstrates the value of serendipity in science. Hoag's discovery was accidental, a result of careful examination of photographic plates. Many of astronomy's greatest discoveries, pulsars, quasars, cosmic microwave background, arose from unexpected observations. Hoag's object reminds us to look carefully at data, to question assumptions, and to follow curiosity wherever it leads. Furthermore, Hoag's object illustrates the power of multi-wavelength astronomy. No single wavelength reveals the full story. Optical images show the ring's stars. Radio observations map the gas. Infrared penetrates dust, and X-rays probe hot plasma. Only by combining data across the electromagnetic spectrum can we construct a complete picture. This holistic approach is now standard in astronomy, but Hoag's object was among the systems that helped establish its importance. The galaxy also serves an educational role. Its striking appearance makes it an ideal subject for public outreach, capturing imagination and sparking interest in astronomy. Images of Hoag's object appear in textbooks, planetarium shows, and popular science articles, introducing countless people to the wonders of the universe. Its beauty is not merely aesthetic, it is a gateway to deeper understanding. For professional astronomers, Hoag's object is a benchmark, a test case for models and theories. Any comprehensive theory of galaxy formation must be able to explain Hoag's object's existence, even if such objects are rare. Theories that cannot account for Hoag's object are incomplete, missing physics or mechanisms necessary for a full description of galactic diversity. Finally, Hoag's object embodies the spirit of scientific inquiry, the drive to understand the universe in all its complexity and strangeness. It stands as a monument to human curiosity, a reminder that the cosmos contains wonders beyond our imagination, structures that shouldn't exist, but somehow do. The spectroscopic signatures of disruption. When astronomers turn spectrographs toward Hoag's object, they're not merely cataloguing wavelengths, they're reading a fossil record written in light. Every photon carries information about the atoms that emitted it, their temperature, velocity, chemical composition, and physical state. For Hoag's object, spectroscopic analysis reveals subtle anomalies that hint at violent processes lurking beneath the structure's serene appearance. The ring's spectrum displays strong hydrogen alpha emission, the signature of ionized hydrogen gas heated by ultraviolet radiation from young stars. This emission is expected in star-forming regions, but its intensity distribution across the ring tells a more complex story. Rather than peaking uniformly, the emission shows localized enhancements corresponding to individual star-forming regions separated by quieter zones. This patchiness suggests that star formation proceeds in bursts, with regions igniting and fading on timescales of tens of millions of years. Absorption features in the spectrum dark lines, where specific wavelengths have been removed by atoms, absorbing light to provide complementary information. Strong absorption from calcium and sodium indicates the presence of cooler stellar atmospheres, while weaker iron and magnesium lines trace intermediate temperature stars. The relative strengths of these features constrain the stellar population's age distribution. In Hoag's object's ring, the absorption spectrum is consistent with a mix of stars spanning several 100 million years, confirming ongoing rather than instantaneous star formation. The core's spectrum contrasts sharply. It shows weak or absent hydrogen alpha emission, indicating little or no ionized gas, and thus no active star formation. Instead, absorption features dominate, particularly those associated with red giants and evolved stars. The magnesium absorption line at 5,175 angstroms is especially prominent, a hallmark of old stellar populations. This spectroscopic signature confirms that the core exhausted its gas supply billions of years ago, transitioning into a quiescent state long before the ring formed. Velocity measurements extracted from spectral line shifts reveal the system's dynamics in exquisite detail. The ring rotates with velocities reaching 250 km per second at its inner edge, gradually decreasing to 200 km per second at the outer edge. This differential rotation follows a nearly Keplerian profile, where velocity decreases with distance, as expected for orbits dominated by a central mass concentration. However, subtle deviations from pure Keplerian motion indicate the presence of additional mass distributed throughout the ring, and halo-likely dark matter contributing to the gravitational potential. The core exhibits different kinematics. Velocity dispersion measurements, quantifying the random motions of stars, show that core stars move in all directions, with speeds around 150 km per second, characteristic of pressure-supported systems rather than rotationally supported disks. This random motion pattern is typical of elliptical galaxies and confirms that the core lacks organized rotation, its stellar orbit scrambled by past violent events. Chemical abundance ratios derived from spectroscopy provide additional constraints. The ratio of alpha elements like oxygen and magnesium to iron traces star formation timescales. High alpha to iron ratios indicate rapid star formation, where massive stars exploding as supernovae enriched gas with alpha elements before lower mass stars could contribute iron through delayed supernova types. In Hoag's object's core, elevated alpha to iron ratios suggest intense early star formation followed by rapid quenching, consistent with formation through major mergers that triggered starbursts before expelling remaining gas. The ring shows lower alpha to iron ratios, indicating more gradual chemical enrichment. This difference suggests the ring's gas experienced extended processing through multiple generations of stars before accumulating in its current location, or that it incorporated material from a distinct source with different enrichment history. Determining which scenario applies requires detailed modeling, comparing observed abundance patterns to predictions from galactic chemical evolution models. Emission from ionized metals, particularly doubly ionized oxygen, visible as the greenish OIIE doublet traces gas physical conditions. The OIII to hydrogen beta ratio is sensitive to gas temperature and ionization state, which depend on the intensity of ultraviolet radiation from massive stars. In Hoag's object, this ratio varies across the ring, with higher values near bright star clusters where radiation is most intense. These variations map the feedback processes through which massive stars regulate their environment, ionizing and heating surrounding gas. Spectroscopic observations also search for signatures of the hypothetical intruder galaxy. If remnants of the intruder survive within Hoag's object's halo, they should display distinct velocity patterns, stars moving on different orbital trajectories than the native population. Deep spectroscopic surveys targeting faint outer regions could identify such kinematically distinct components, though none have been conclusively detected. The absence of obvious intruder signatures suggests either complete disruption or that the intruder has traveled beyond survey boundaries. Molecular gas and the future of star formation. Beyond neutral hydrogen, molecular gas represents the immediate fuel for star formation. Molecular clouds, vast aggregations of hydrogen molecules bound by gravity, are the birthplaces of stars. Understanding Hoag's object's molecular gas content and distribution is essential for predicting its evolutionary future and determining how long star formation can continue in the ring. Detecting molecular hydrogen directly is challenging because the molecule lacks strong emission lines at radio wavelengths under typical interstellar conditions. Instead, astronomers use carbon monoxide as a tracer. CO emits strongly at millimeter wavelengths and tracks molecular gas with reasonable accuracy, though conversion factors between CO luminosity and total molecular mass carry uncertainties. Observations of Hoag's object using millimeter telescopes reveal CO emission concentrated in the ring, confirming molecular gas presence. The total molecular mass is estimated at several hundred million solar masses, comparable to or slightly less than the neutral hydrogen mass. This relatively low molecular to atomic gas ratio suggests that much of the ring's gas remains atomic rather than condensed into molecules, a state typical of outer galactic disks, where gas densities are lower and ultraviolet. Radiation from stars dissociates molecules. The molecular gas distribution within the ring is clumpy, mirroring the neutral hydrogen structure. Individual molecular clouds have masses ranging from millions to tens of millions of solar masses, similar to giant molecular clouds in spiral galaxies like the Milky Way. These clouds are gravitationally bound and provide the sites where stars actually form. The cloud's velocity widths measuring internal turbulence indicate supersonic motions driven by stellar feedback, supernova explosions, and gravitational collapse. The star formation efficiency, the fraction of molecular gas converted into stars per unit time, can be estimated by comparing star formation rates to molecular gas masses. For Hoag's object's ring, the efficiency is roughly 1% per 100 million years, similar to normal spiral galaxies. This similarity suggests that despite the unusual galactic structure, star formation proceeds through standard mechanisms once molecular clouds form. The ring's geometry does not fundamentally alter the physics of star formation at molecular cloud scales. Molecular gas observations also constrain the ring's future evolution. At current star formation rates, the molecular gas supply will be exhausted within a few billion years. However, this estimate assumes no gas replenishment. If atomic hydrogen continues condensing into molecules, or if gas accretes from intergalactic space, star formation could persist longer. Conversely, if stellar feedback expels gas faster than it condenses, star formation will cease earlier. The spatial correlation between molecular gas and young stars is strong but imperfect. Some molecular clouds show no associated star formation, while some stellar regions lack detected molecular gas. These mismatches reflect the star formation cycle's different phases. Molecular clouds exist for tens of millions of years before forming stars. Once stars form, their ultraviolet radiation and stellar winds dissociate and disperse surrounding molecular gas within a few million years. Observations capture this process at various stages, producing the observed spatial variations. Comparing molecular gas properties in the ring to those in the gap reveals stark differences. The gap contains little or no detected molecular gas, consistent with its low stellar density and absence of star formation. This deficit confirms that the gap is not merely a projection effect, but a genuine physical void where gas has been removed or prevented from accumulating. The core similarly lacks molecular gas. Upper limits from non-detections indicate molecular masses below tens of millions of solar masses, orders of magnitude less than the ring. This absence explains the core's quiescence and supports scenarios where the collision that formed the ring also stripped or expelled the core's gas, preventing further star formation. Molecular gas kinematics provide additional dynamical constraints. The molecular clouds rotate with the ring, sharing the same velocity pattern as neutral hydrogen and stars. This kinematic coherence indicates that molecular clouds are gravitationally bound to the ring rather than transient features. The cloud's internal velocity dispersions, however, show that they are turbulent and dynamic, constantly stirred by internal and external forces. Future observations with more sensitive millimeter telescopes, particularly the Atacama Large Millimeter Array, could map molecular gas at higher resolution, resolving individual clouds and measuring their properties in detail. Such observations would determine whether molecular clouds in the ring differ systematically from those in normal spiral galaxies, potentially revealing how ring geometry influences cloud formation and evolution. The stellar halo's hidden history. Surrounding Hoag's object's bright ring and core lies a vast stellar halo, a diffuse distribution of stars extending hundreds of thousands of light-years into space. This halo is faint, containing perhaps only a few % of the galaxy's total stellar mass, but it holds crucial clues about Hoag's object's formation history and past interactions. Stellar halos form through multiple processes. Stars can be scattered from the main galactic body during violent events like mergers. Satellite galaxies tidally disrupted while orbiting a larger galaxy deposit their stars into the halo. Globular clusters gradually lose stars through gravitational interactions, populating the halo with old, metal-poor stars. Each process leaves distinct signatures in the halo's structure, kinematics, and stellar populations. Deep imaging of Hoag's object's outer regions reveals faint, extended emission beyond the ring's sharp outer edge. This emission is consistent with a stellar halo, though measuring its precise properties is challenging due to contamination from foreground stars in our own Milky Way and background galaxies at greater distances. Careful photometric analysis, selecting stars by color and brightness, can statistically separate halo stars from contaminants. But individual star identification requires spectroscopy. The halo's color suggests an old stellar population, dominated by red giants and main sequence turn-off stars billions of years old. This age is consistent with halo formation early in the galaxy's history, perhaps during the mergers that created the core. Younger stars are rare or absent in the halo, indicating that recent star formation has been confined to the ring rather than occurring throughout the system. Measuring the halo's metallicity distribution provides insights into its origins. If the halo formed primarily through early mergers, it should display a range of metallicities, reflecting the diverse progenitors that contributed stars. If it formed through later accretion of satellite galaxies, the metallicity distribution might show distinct peaks corresponding to different accretion events. Current observations lack sufficient precision to definitively distinguish these scenarios, but future spectroscopic surveys targeting individual halo stars could resolve the ambiguity. The halo's spatial structure is nearly spherical, lacking the flattened geometry of the ring or disk-like features. This spherical distribution is typical of galactic halos and reflects the randomized orbits of halo stars, which have been dynamically heated through gravitational interactions over billions of years. The absence of prominent substructure streams or shells indicating recent accretion suggests that Hoag's object has not experienced major mergers in the recent past, aside from the event that created the ring. However, subtle asymmetries in the halo's density distribution could indicate older, partially phase-mixed tidal streams. When a satellite galaxy is disrupted, its stars initially form a coherent stream following a specific orbit. Over time, gravitational perturbations spread the stars along the orbit, eventually wrapping the stream multiple times around the host galaxy. After billions of years, streams become so dispersed they appear as smooth halo components. Detecting such ancient streams requires ultra-deep imaging and statistical analysis to identify overdensities against the smooth background. The halo's total mass, though uncertain, is estimated at tens of billions of solar masses, based on surface brightness, extrapolations and comparisons to similar galaxies. This mass is small compared to the core and ring, but significant enough to affect the system's overall gravitational potential. The halo's mass contributes to the rotation curve at large radii, though distinguishing halo contributions from dark matter is nearly impossible without detailed stellar kinematics. Globular clusters associated with Hoag's object's halo provide additional probes of its history. Globular clusters are ancient stellar systems containing hundreds of thousands to millions of stars, formed during the early universe's most intense star formation epochs. Their properties, ages, metallicities, spatial distributions reflect their host galaxy's formation history. Unfortunately, detecting individual globular clusters around Hoag's object is difficult given its distance. Only the brightest, most massive clusters are visible, and comprehensive surveys have not been conducted. The halo's connection to the ring-forming collision is uncertain. If the collision was sufficiently violent, it could have scattered stars from the original disk into the halo, adding a younger component to the otherwise ancient population. Alternatively, the collision might have had minimal impact on the halo, leaving it largely undisturbed. Distinguishing these possibilities requires measuring age distributions and kinematics of halo stars at various positions. Data currently unavailable. Infrared windows into hidden processes. While optical observations capture the bright blue stars that define Hoag's object's ring, infrared wavelengths reveal complementary information about cooler components, red giants, dust, and warm molecular gas. Infrared astronomy has transformed our understanding of galaxy evolution by penetrating dust that obscures optical light and detecting emission from stars and gas at intermediate temperatures. Near-infrared observations at wavelengths around 1 to 2 micrometers trace the evolved stellar populations that dominate galactic mass. Red giants, stars in late evolutionary stages burning helium in their cores, emit most strongly in near-infrared. In Hoag's object, near-infrared imaging reveals that the core's luminosity is dominated by such stars, confirming its old age. The ring also contains red giants mixed with younger blue stars, indicating continuous star formation over extended periods rather than a single starburst. The near-infrared light distribution differs subtly from optical. The core appears relatively brighter in infrared, reflecting the fact that old stellar populations emit more efficiently at longer wavelengths. This shift affects mass-to-light ratios, the relationship between a galaxy's luminosity and its stellar mass. Infrared-derived mass estimates are typically more accurate than optical because they weigh old stars, which comprise most galactic mass, more heavily. Mid-infrared observations at wavelengths around 5 to 30 micrometers probe warmer dust heated by stellar radiation and emission from aromatic hydrocarbon molecules. Dust grains in the interstellar medium absorb ultraviolet and optical light from stars, heating to temperatures of tens to hundreds of Kelvin. This absorbed energy is re-radiated in mid-infrared, making dusty regions glow even when invisible optically. In Hoag's object's ring, mid-infrared emission correlates with star-forming regions, indicating dust heated by massive young stars. The infrared luminosity provides an independent star formation rate estimate, particularly valuable because it captures star formation obscured by dust. Comparing infrared and ultraviolet star formation rates reveals that dust obscuration is modest in Hoag's object. Most star formation is visible optically, consistent with the ring's relatively low gas surface density. The infrared spectrum contains emission features from polycyclic aromatic hydrocarbons, PAHs, complex carbon molecules produced in stellar atmospheres and interstellar chemistry. PAH emission traces regions where ultraviolet radiation from stars excites these molecules, without destroying them, typically in photodissociation regions at the edges of molecular clouds. In Hoag's object, PAH emission follows the ring's star-forming regions, confirming active feedback processes where stellar radiation regulates surrounding gas. Far infrared observations at wavelengths beyond 30 micrometers detect cooler dust at temperatures around 20 to 30 Kelvin. This cold dust resides in molecular clouds not yet forming stars, representing reservoirs of potential future star formation. Measurements of far infrared emission in Hoag's object's ring constrain the cold gas mass. Complementing CO observations, the far infrared-derived gas masses generally agree with CO-based estimates, validating the molecular gas measurements. Infrared imaging also searches for hidden stellar populations in the gap between ring and core. If the gap contains significant numbers of old, cool stars, perhaps remnants of the original disk, they would emit in near-infrared, while remaining faint optically. Deep near-infrared surveys have detected some stars in the gap, but their density is far lower than in either the ring or core, confirming that the gap is a genuine underdensity rather than an optical illusion. The core's infrared properties provide insights into its stellar population's detailed characteristics. Infrared colors, ratios of emission at different wavelengths, are sensitive to stellar ages and metallicities. Hoag's object's core shows infrared colors typical of old, metal-rich stellar populations, consistent with formation through early mergers involving gas-rich progenitors that had already undergone substantial chemical enrichment. Spitzer Space Telescope and Herschel Space Observatory observations have mapped Hoag's object's infrared emission, though spatial resolution remains limited compared to optical imaging from Hubble. Future infrared missions, particularly the James Webb Space Telescope, offer unprecedented resolution and sensitivity. JWST observations could resolve individual star clusters in the ring at near-infrared wavelengths, measure their ages and masses precisely, and detect faint stellar populations in the halo and gap missed by previous surveys. Infrared spectroscopy provides yet another diagnostic. Emission lines from ionized gas at infrared wavelengths, particularly fine structure lines like oxygen and neon, trace gas, physical conditions complementary to optical lines. These lines are less affected by dust extinction and probe different gas phases. Future infrared spectroscopic observations could map gas conditions throughout the ring, revealing how stellar feedback regulates the star formation cycle. Numerical simulations and theoretical models. Understanding Hoag's object's formation requires more than observations. It demands detailed theoretical models that can reproduce the observed structure and predict its evolution. Numerical simulations, which solve the equations of gravity and hydrodynamics for millions of particles representing stars, gas, and dark matter, provide the primary tool for testing formation scenarios. Early simulations of galactic collisions date to the 1970 when pioneering work by Allard and Jury Toumre demonstrated that tidal interactions could produce the spectacular shapes of interacting galaxies. These simulations used restricted n-body codes, tracking only gravitational forces between particles representing stars and dark matter. Gas dynamics were omitted or treated crudely, limiting the model's realism. Modern simulations are far more sophisticated. They employ smoothed particle hydrodynamics, SPH, or adaptive mesh refinement, AMR techniques, to solve gas dynamics equations, tracking pressure forces, shock heating, and radiative cooling. Star formation is modeled using prescriptions that convert gas into stellar particles when density and temperature thresholds are met. Stellar feedback energy and momentum injection from supernovae and stellar winds is included to regulate star formation and drive outflows. Simulating a bullseye collision, like the one hypothesized for Hoag's object, requires careful setup. The target galaxy is constructed with a rotating disk of gas and stars embedded in a dark matter halo, representing a typical spiral galaxy. The intruder is a smaller galaxy launched on a trajectory passing directly through the target's center. The impact velocity, intruder mass, and target structural parameters are varied to explore the parameter space. When parameters are tuned correctly, simulations produce ring structures qualitatively similar to Hoag's object. The intruder's passage generates a circular shockwave that propagates outward through the target's disk, compressing gas and pushing it radially. As gas accumulates at a characteristic radius, determined by the collision's energy, it cools and forms stars, creating the observed ring. The target's original disk is disrupted, with inner portions settling into the core and outer portions forming the ring. However, achieving quantitative agreement is challenging. Simulated rings often display asymmetries, or multiple rings, not present in Hoag's object. The collision's geometry must be extraordinarily precise. Deviations of even a few degrees from perfect alignment produce noticeable distortions. This fine-tuning raises questions about how such collisions occur naturally, given the randomness of galactic encounters. One approach to resolving this puzzle invokes dynamical friction. When galaxies orbit within a shared dark matter halo, their motion through the halo creates gravitational drag that circularizes orbits and promotes aligned encounters. Simulations including dynamical friction show that initially inclined orbits can evolve toward equatorial configurations over hundreds of millions of years, increasing the probability of bullseye impacts. This mechanism may explain how Hoag's object's collision achieved such precise alignment. Alternative formation scenarios have been tested through simulations. One model proposes that the ring formed not through a collision, but through gravitational instability in a rapidly rotating disk. If a disk spins fast enough, centrifugal forces can overcome gravity at certain radii, creating gaps or rings. However, this requires specific rotation profiles and disk masses that are difficult to establish through standard galaxy formation processes. Another model suggests accretion of gas from intergalactic space into a ring orbit around an existing galaxy. If gas falls in with specific angular momentum, it naturally settles into a ring rather than spreading throughout a disk. Simulations show this can produce ring-like structures, but typically with less defined gaps and lower star formation rates than observed in Hoag's object. Comparing simulations to observations requires generating synthetic observations, predictions of what telescopes would detect if pointed at simulated galaxies. This involves calculating emission at various wavelengths based on simulated stellar populations and gas properties, accounting for dust extinction and instrumental effects. Synthetic observations can then be directly compared to real data, testing whether simulations reproduce not just qualitative features, but quantitative measurements like surface brightness profiles, colors, and rotation curves. For Hoag's object, published simulations have achieved reasonable agreement with overall structure, but struggle to match finer details. The ring's near-perfect circularity remains difficult to reproduce, suggesting either missing physics in simulations or observational biases that make the ring appear more symmetric than it truly is. Resolving this requires both improved simulations and better observational constraints. Simulations also predict future evolution. In most models, rings gradually collapse inward over several 100 million years as stars and gas lose angular momentum through gravitational interactions. The ring's stars spiral toward the core, eventually merging with it to form a larger elliptical galaxy. Hoag's object's current appearance represents a snapshot during this transient phase, explaining why such structures are rare. Hoag's object in the cosmic census. Every galaxy discovered adds a data point to astronomy's grand census, a comprehensive effort to catalogue and understand the universe's galactic population. Hoag's object, despite being unique, fits within broader patterns of galaxy diversity that reveal fundamental principles of structure, formation, and evolution. Placing Hoag's object in this cosmic context illuminates not just its individual peculiarities, but what it teaches about galactic physics generally. Large-scale galaxy surveys have catalogued hundreds of millions of galaxies across vast cosmic volumes. These surveys reveal that galaxies follow certain distributions in properties like mass, size, color, and morphology. The mass function, the number of galaxies per unit mass, shows that low-mass galaxies vastly outnumber massive ones, following a power law that reflects hierarchical structure formation, where small structures form first and merge to build larger ones. Hoag's object sits near the high-mass end of the galaxy mass function, with total mass comparable to the Milky Way's. Such massive galaxies are relatively rare, comprising a small fraction of the total galaxy population. Their rarity reflects the challenge of assembling large amounts of matter through gravitational collapse and mergers over cosmic time. Morphologically, galaxies divide into categories: spirals with rotating disks and prominent arms, ellipticals with smooth light distributions and random stellar orbits, and irregulars lacking coherent structure. The Hubble tuning fork diagram organizes these categories, with spirals branching between barred and unbarred varieties, and ellipticals graded by ellipticity. Ring galaxies like Hoag's object occupy a tiny niche outside the main classification scheme, representing rare evolutionary pathways. The color magnitude diagram provides another organizing principle. Galaxies segregate into a red sequence of quiescent ellipticals and early-type spirals with old stellar populations, and a blue cloud of actively star-forming late-type spirals and irregulars. Hoag's object straddles this division. Its core is red, placing it on the red sequence, while its ring is blue, belonging to the blue cloud. This duality reflects its composite nature, combining components with distinct formation histories and evolutionary states. Galaxy environments influence morphology and evolution. Dense clusters contain predominantly ellipticals and S0 galaxy spirals that have lost gas through interactions or ram pressure stripping. Low-density field environments favor spirals and irregulars with active star formation. Hoag's object resides in a relatively low-density environment, intermediate between isolated field galaxies and rich clusters. This environment may have facilitated the collision that formed the ring while preventing subsequent interactions that would disrupt it. Scaling relations connect galaxy properties, revealing underlying physical principles. The Tully-Fisher relation links spiral galaxies' rotation velocities to luminosities, reflecting the connection between mass and light. The fundamental plane relates elliptical galaxies' sizes, surface brightnesses, and velocity dispersions, constraining stellar population properties and mass-to-light ratios. Hoag's object's core follows the fundamental plane, while its ring's rotation follows a relation similar to Tully-Fisher, confirming that despite unusual structure, it obeys fundamental gravitational scaling. The galaxy stellar mass function's evolution with redshift, looking back through cosmic time, reveals when and how galaxies assembled mass. High redshift surveys show that massive galaxies were rarer in the early universe, with the population growing through mergers and accretion. The cosmic star formation rate peaked around redshift 2 when the universe was roughly 3 billion years old, then declined to present levels. Hoag's object's formation likely postdates this peak, occurring during the era of declining star formation, when galaxy collisions became less frequent. Rare objects like Hoag's object challenge theoretical models to explain outliers, not just typical cases. A successful galaxy formation theory must account for the full diversity of observed galaxies, from common spirals to exotic ring galaxies. Models focusing only on average properties miss physics essential for understanding transient evolutionary phases and unusual configurations. Statistical studies of ring galaxies as a class provide population-level insights. By determining how many ring galaxies exist per unit volume and their properties distributions, astronomers constrain collision rates, geometries, and environmental dependencies. Current estimates suggest ring galaxies comprise roughly 0.01% of all galaxies, 1 in 10,000, a fraction consistent with bullseye collision rates predicted from dynamical models. Hoag's object's isolation. Within this rare population, its exceptional symmetry and lack of companions makes it an outlier among outliers, perhaps the most extreme example yet discovered. Whether this reflects observational selection effects or genuine physical extremity remains uncertain. Future surveys discovering more ring galaxies will clarify whether Hoag's object represents one end of a continuous distribution or a truly unique configuration. The cosmic census ultimately aims to reconstruct galaxy evolution pathways, tracking how galaxies form, grow, interact, and age across cosmic history. Hoag's object marks a specific point along one pathway, a transient phase between a normal spiral's collision and eventual merger into an elliptical. Understanding this pathway requires studying many systems at various stages, from pre-collision spirals through ring galaxies like Hoag's object to post-merger ellipticals. Each system provides snapshots of evolution's continuous process, which simulations stitch into coherent narratives spanning billions of years. X-ray echoes of violent history. Beyond the visible and infrared wavelengths that reveal stars and gas, X-ray observations probe the universe's most energetic phenomena. Hot plasmas heated to millions of degrees, matter falling into black holes, and the aftermath of violent explosions. For Hoag's object, X-ray astronomy offers a window into processes invisible at other wavelengths, potentially uncovering evidence of the catastrophic collision that shaped its structure. X-ray emission from galaxies arises from multiple sources. X-ray binaries systems, where a compact object like a neutron star or black hole accretes matter from a companion star, produce intense X-ray emission as infalling matter heats to temperatures exceeding 10 million Kelvin. Supernova remnants glow in X-rays as expanding shockwaves heat surrounding gas. Hot interstellar plasma, particularly in elliptical galaxies and galaxy clusters, emits thermal X-ray radiation through Bremsstrahlung and line emission from highly ionized atoms. Observations of Hoag's object with X-ray telescopes like Chandra X-ray Observatory and XMM Newton reveal faint X-ray emission from multiple sources. The most prominent emission originates from the core region, consistent with a population of X-ray binaries and possibly low-level activity from the central supermassive black hole. The X-ray luminosity is modest, roughly 1 billion times the Sun's bolometric luminosity, indicating that the core is quiescent rather than hosting an active galactic nucleus. The distribution of X-ray point sources traces stellar populations. Young stellar populations produce high-mass X-ray binaries, where massive stars donate matter to compact companions. These systems are short-lived, fading within tens of millions of years as the massive donors exhaust their fuel and explode. Old stellar populations instead harbor low-mass X-ray binaries, where evolved stars like red giants transfer matter to neutron stars or black holes. These systems persist for billions of years, accumulating over time. In Hoag's object, X-ray point sources in the ring likely represent high-mass X-ray binaries associated with recent star formation, while core sources are predominantly low-mass systems reflecting the ancient stellar population. The number of detected sources, roughly a dozen in available observations, is consistent with expectations based on the stellar masses and ages, providing no evidence for unusual X-ray populations. More intriguing is the possibility of diffuse X-ray emission from hot gas. If the collision that created the ring was sufficiently energetic, it would have shock-heated gas to X-ray emitting temperatures. This hot gas should be distributed throughout the system, particularly in regions where colliding gas streams intersected. However, detecting diffuse emission is challenging because it is faint and extended, easily confused with instrumental background and contaminating foreground emission from our galaxy. Deep X-ray observations targeting Hoag's object specifically to search for diffuse emission have not been conducted, leaving this question unresolved. Existing archival observations, while sufficient to detect bright point sources, lack the sensitivity and spatial coverage to definitively confirm or rule out hot, gaseous halos. Future deep observations could reveal whether Hoag's object retains a reservoir of shock-heated gas from the collision, or whether such gas has cooled and condensed or been expelled through feedback processes. The central supermassive black hole's X-ray emission provides constraints on its current accretion state. Most supermassive black holes in quiescent galaxies emit weakly, accreting only small amounts of material from their surroundings. Hoag's object's core shows X-ray emission consistent with such low-level accretion, producing luminosities far below those of active galactic nuclei. This quiescence suggests that gas was efficiently expelled or consumed during earlier evolutionary phases, leaving little fuel for current black hole growth. X-ray spectroscopy, when sufficient photons can be collected, provides insights into gas temperatures, ionization states, and metal abundances. For Hoag's object, limited photon statistics preclude detailed spectral analysis, but future observations could measure the hot gas temperature and metallicity if diffuse emission is detected. High metallicities would indicate that hot gas originated from processed stellar material ejected by supernovae, while lower metallicities might suggest primordial gas shocked during the collision. Temporal variability in X-ray emission offers another diagnostic. X-ray binaries often exhibit variability on timescales, from seconds to years, as accretion rates fluctuate. Monitoring Hoag's object's X-ray sources over time could identify transient sources, systems that brighten temporarily during outbursts, and constrain binary populations more accurately. Similarly, the central black hole might show variability if accretion rates change, though current observations lack the temporal coverage to detect such variations. Comparing Hoag's object's X-ray properties to other ring galaxies reveals common patterns. The Cartwheel Galaxy, for instance, shows enhanced X-ray emission from its ring, where active star formation produces numerous high-mass X-ray binaries. Hoag's object's more modest X-ray luminosity reflects its lower star formation rate, consistent with a more evolved system where the initial collision-triggered starburst has subsided. The absence of strong X-ray emission from the gap between ring and core is noteworthy. If significant amounts of hot gas persisted in this region, it would emit detectably in X-rays. The non-detection suggests either that gas was efficiently swept into the ring during the collision, leaving the gap evacuated, or that any residual gas has cooled below X-ray emitting temperatures. This absence supports models where the gap represents a genuine underdensity rather than a region filled with undetected material. X-ray observations also constrain the dark matter distribution indirectly. In galaxy clusters, X-ray emission from hot intracluster gas traces the gravitational potential, allowing dark matter measurements through hydrostatic equilibrium assumptions. While Hoag's object lacks sufficient hot gas for such analysis, future detection of diffuse X-ray emission could enable similar techniques, providing independent mass estimates complementary to rotation, curve, and lensing measurements. The environmental context and cosmic neighborhood. No galaxy exists in isolation. Each resides within a cosmic web of structure, a vast network of filaments, sheets, and voids, shaped by dark matter's gravitational influence over billions of years. Understanding Hoag's object requires examining its environmental context, the nearby galaxies, large-scale structures, and cosmic flows that influenced its formation and continue shaping its evolution. Galaxy formation theories distinguish between nature and nurture intrinsic properties determined by initial conditions versus environmental influences from surroundings. Galaxies in dense clusters experience frequent interactions, ram pressure stripping as they move through hot intracluster gas, and tidal forces from the cluster's gravitational potential. These processes transform spirals into ellipticals, quench star formation, and alter morphologies. Isolated field galaxies evolve more quiescently, avoiding such perturbations. Hoag's object occupies an intermediate environment. It is not part of a rich galaxy cluster, avoiding the most extreme environmental effects. However, it is not completely isolated either, residing in a region with nearby galaxies that could have influenced its history. The nearest confirmed neighbors lie several million light-years away, close enough that gravitational interactions over cosmic timescales are possible, yet distant enough that current interactions are weak. This semi-isolation is actually favorable for ring galaxy formation. In dense clusters, high relative velocities between galaxies produce collisions too energetic for ring formation. Intruders pass through too quickly, generating weak shockwaves insufficient to create well-defined rings. In extremely isolated environments, encounter rates are so low that collisions rarely occur. Intermediate density environments like Hoag's objects provide the right balance. Collision velocities moderate enough for efficient ring formation, yet encounters frequent enough that bullseye impacts occasionally happen. Mapping the three-dimensional distribution of galaxies around Hoag's object requires spectroscopic redshift surveys. Redshifts measure how much light has been stretched by cosmic expansion, translating directly to distance given Hubble's law. Surveying galaxies within tens of millions of light-years of Hoag's object would reveal whether it belongs to a galaxy group, filament, or relatively empty void region. Existing surveys provide limited coverage of Hoag's object's neighborhood. The Sloan Digital Sky Survey and other large programs have measured redshifts for thousands of galaxies in the surrounding sky region. But many faint or small galaxies remain unmeasured. Preliminary analysis suggests Hoag's object is not part of a compact group, but rather lies in a lower density filament connecting larger structures. This environment is typical for galaxies of its mass, consistent with hierarchical structure formation predictions. The local velocity field, the pattern of galaxy motions relative to cosmic expansion, provides additional environmental information. Galaxies do not move solely with the Hubble flow, but also experience peculiar velocities caused by gravitational attraction toward overdense regions and repulsion from voids. Measuring these peculiar velocities maps the underlying dark matter distribution, revealing large-scale structures invisible in galaxy counts alone. For Hoag's object, peculiar velocity estimates are uncertain due to limited measurements of nearby galaxies. However, its recession velocity is consistent with Hubble flow expectations given its distance, suggesting no strong gravitational pull from nearby massive structures. This reinforces the picture of relative isolation, where Hoag's object evolved without dominant external influences after the ring-forming collision. The cosmic web's filamentary structure channels galaxy encounters. Galaxies tend to move along filaments, increasing collision probabilities compared to random distributions. If Hoag's object and its intruder both orbited within the same filament, their encounter would be more likely than if they approached from unrelated directions. Testing this requires reconstructing the intruder's trajectory and determining whether it originated from the same large-scale structure as the target galaxy. Environmental influences extend to gas content. Galaxies can accrete gas from the intergalactic medium, replenishing star formation fuel, or lose gas through ram pressure as they move through diffuse intergalactic gas. For Hoag's object, current gas accretion rates are unknown, but likely modest given the low density of surrounding intergalactic gas. Gas loss through ram pressure is similarly negligible unless Hoag's object is moving rapidly through a gaseous medium, which observations do not suggest. The broader cosmological context also matters. Hoag's object formed when the universe was roughly 13 billion years old, during an era when cosmic structure had matured significantly. The peak epoch of galaxy mergers and interactions occurred several billion years earlier, when galaxies were more densely packed. By the time Hoag's object's ring formed, collision rates had declined, making such events rarer. This timing explains why ring galaxies are uncommon. We observe a universe past its most dynamically active phase. Future evolution depends on environmental factors. If Hoag's object remains isolated, it will evolve quiescently, with the ring gradually collapsing and star formation declining as gas is exhausted. If it encounters another galaxy, the ring could be disrupted, triggering new interactions that reshape the system again. The probability of such encounters depends on the local galaxy density and velocity dispersion, quantities that environmental studies constrain. Wide-field surveys planned for coming decades will map Hoag's object's environment in unprecedented detail. Rubin Observatory's legacy survey of space and time will image billions of galaxies, measuring photometric redshifts and positions that reveal large-scale structure. Future spectroscopic surveys will measure precise redshifts for millions of galaxies, mapping the cosmic web in 3 dimensions. These observations will place Hoag's object within the broader cosmic context, revealing how its environment influenced formation and what future holds as the universe continues expanding and evolving.